All right. So anyhow, just a couple announcements because this is important moving forward. There's no class Thursday or Friday because of the holiday. Just so you guys know. So anyhow, we need to pick up where we left off last class, and that was with the comparison test. So if you look at the most recent homework, it's sort of an overwhelming one. I basically just gave you a bunch of series, and I'm asking you to tell me whether they converge or diverge. And then I'm also asking you another subtlety, if you can tell me what the sum is to do it. So this is a challenging homework. It takes a while for us to learn this stuff if we choose to learn it. And so, you know, you should expect that for most of us, it's going to take some effort to make sense of this homework. So with that in mind, we're going to just pick up with where we left off last class. And so what we've been doing is we've been working on convergence test. So the last one we covered what's called the comparison test. Last class. So the comparison test has a close relative that's worth stating.
Wait, why don't we have class Thursday or Friday?
Because it's Easter, and Roche is a Catholic university, and there's no classes Thursday, Friday, or Monday. Now, of course, Daryl, if you would like, I will log on to Zoom and entertain you with shenanigans on Thursday and Friday. But I would assume you guys have other things you can catch up on in these crazy times of the quarantine life.
I don't know. We've been doing the quarantine clean here, and
that's what I was going to say. There's more clean things in this house than there's ever been. Although it's kind of rough with 2 children. So, I don't know why I wrote R here. I don't know what I was getting at. So last class we covered the comparison test. So what we want to do today is we want to start with a close relative of the comparison test. So so this is one that's very useful in many times. Is the so-called limit comparison test. So it sounds very similar. So let's change colors, but whoa. So it's not called the it's not called the comparison test. It's called the limit comparison test.
Can you go back one slide, please?
Sure, I can. Let me know when you're ready.
I'm finished.
Okay, anybody else? Okay, so the comparison test essentially said if we have a series that looks similar to a known series, we can try to use an inequality to get information. The limit comparison test says something very much similar. It says if you have a series that looks like a series you know, perhaps you can gain information by taking a limit. So here's what you need for the hypothesis. So assume you need 2 series, one that you know about and one you want to learn about. Oh my God, do you hear that?
Dinosaurs, man.
I know, right? So we have two series, and what we're going to do is we're just going to write, you know, we don't always have to, you know, if it's understood that these are infinite series, we're not going to write infinity. I mean, I guess we could, but you don't always have to write k equals 1 to infinity under these things. So assume we have two series with positive terms, and that's very important that we have this positive terms. So the thing we want to do is we want to compute something. So we want to compute, and we'll call it L for lack of a better word. We want to compute a certain limit. We're going to take the limit of the terms of the ratio. So we have two series. All the terms are positive. There's no negative numbers. And what we'd like to do is we'd like to ask, okay, suppose we know A converges. Is there anything we could say about B and vice versa? And it turns out that in many cases you can if you study this limit. So that's what we want to look at. So we have three scenarios. Number one, if this limit exists, if it's a number, then the series converge. Or diverge. So that might seem kind of sort of vague, but it's not vague, because if you know one of them already converges, then if that limit exists, then you know the other one converges. Or if you want to use it the other way, if you know one of them diverges, you can use it to prove that the other one diverges. Does anybody have a question about what that might mean? All right, so then the other scenario, if L is 0 and the BK converges, then A sub K converges. And then the last scenario that we can get from this assumption is the following. If L equals infinity and BK diverges, then A sub K diverges. So this theorem's a lot more difficult to state. It's very I shouldn't say more difficult. It's tedious to state. It's very wordy. But in many ways, it's actually a little easier to use. Now, the thing is, much like the comparison test, if you'd like to use this, you have to have some sort of library somewhere of known series that converge or diverge. So that means you need to have in your head things like P series. You need to have things in your head like geometric series. You need to have sort of a catalog, if you will, of known series that converge and diverge. Because if you don't have that, then there's not much you can do with using these tests. The other thing that's often confusing is if you look at the statement of this theorem, if I go back to the original page, a lot of times what you don't realize is if you're comparing two series that have a ratio in them, then this limit is actually the ratio of ratios. So these expressions can get quite complicated as far as fractions are involved. So does anybody have a question about this? Okay. So let's do an example. If I can get some water here first. So let's look at one example before moving on. So one of the standard textbook examples of this is the following series. So if I take the log of k divided by k squared, does this guy converge or diverge? Does anybody have a question?
Is that k squared?
Yeah, I'm sorry. That's a yes, it is k squared. My problem. My problem. My apologies. So one of the issues that comes up when you're studying series like this is, what are you going to use for your comparison? What are you going to compare it to? So this is a very, very interesting series, and it's actually a series that has applications to it. So we want to be sort of how do we handle this problem? So let's look at this solution. So here's the thought process. We know so here's what we know. So let me sort of write it in a different way. Let's change colors. So I have to have a known series. So here's the decision. We know this guy converges. And we know this guy diverges. Now, why am I writing these two things down? Well, because those guys would be the first things that should come to your mind if you want to compare the new series. And also, if you do a little more thinking, you'll say, okay, that the series that I'm trying to study in many ways is living between these two series, the terms at least. So, what's up? Do you need something? So the question is there something that lives between these two things? And when I say live, I'm thinking about the size of each number. So here's one way to think about it. Note the following. Think about what's happening. 1 over k squared is going to be, so how do I get that? Well, I'm noting that log of k is going to be less than k. And so that implies that log of k over k squared is less than or equal to 1 over k. So if you just rewrite that, if I divide both sides by k squared, I get that. Similarly, I know that log of k is greater than 1. And so if I divide both sides by k squared, I get the natural log of k over k squared is greater than 1 over k squared. So what I'm telling you, what I'm trying to get you to understand or to reason is the following. This guy has to be less than this guy. And I guess I should be more specific. This guy has to be less than this guy. So when I say that this guy lives between the two, that's what I mean. And we know this diverges. And we know this converges. So we're trying to think about, okay, so since this guy, it's bigger than a convergent one and it's smaller than a divergent one, we can't make any logical conclusions on what's absolutely happening yet. We have to be a little more technically sound. Change my colors. Okay, so you might think to yourself, okay, so which one should I choose? Should I try to compare it to the one that converges, or should I compare it to the one that diverges? And it turns out that in each one of those cases, you're not going to get any information. So what instead we're going to do is, since it's between them, let's choose something that should be between them. What is a number between 1 and 2? And why am I using 1 and 2? Well, I'm looking at the exponent here and I'm looking at the exponent here. What is the number between 1 and 2 that I might want to study?
1.5.
That's right. So the maybe naive choice is, let's compare with
3/2.
the convergent series. 1 over k to the 3/2. Why? Because 3/2 is less than 2 and it's less than 1. Now, it wouldn't be wrong to try 1 or 2, but if you do that, you're going to get to a dead end. So I'm trying to save us time. And I'm also trying to give you the bigger picture here, why 3/2 might be a good guy to check with. Okay, so what you have to do then is you have to take this limit. So before I go to the next page, does anybody have a comment or a question? Okay, so let's do it. So we compute L is the following limit. So take the limit as k goes to infinity. So we need our a sub k over b sub k. So what's our a sub k? It's log k over k squared. And what's our b sub k? It's 1 over k to the 3/2. Now, if I do a little algebra, this becomes a limit we studied way back in Calc 1. So if I rewrite this, this becomes log of k. Now, if you do this, this becomes nothing more than x, or excuse me, not x. becomes k to the 1/2 if you use your exponent properties. Now, I can't take this limit as it is. If I try to evaluate this limit, I get infinity over infinity, but we had a tool for that, which was called L'Hopital's rule. And L'Hopital says you can differentiate the numerator and the denominator. The derivative of log k is 1 over k. The derivative of the denominator is 1/2 k to the negative 1/2. Wow, that's pretty ugly writing. Let me fix that. So this is 1/2 k to the negative 1/2. And you might not remember L'Hopital's rule, but it is something that you learned in Calculus 1. And so when you take that 1/2 to the top and you take this limit, you end up getting 1 over 2 to the square root of k, and this limit is 0. And so what we can conclude is the following. We'll get out the different color. So we conclude that this guy converges. So this is not an easy problem. It is a challenging example. It's requiring that you have some memory of a lot of these tools that you learned about. But I would encourage you to try to learn it. It's sort of like a nice, once you finally get it, after a while, you're like, hey, okay, great, I got it. Does anybody have a question about this? By the way, these
when you simplify, you just did like cross multiplication, right?
where do you mean that? You mean in this on the screen?
Yeah. When you
I don't like to call it cross multiplication. What I'm saying is I'm taking a fraction and you multiply it by the reciprocal.
Yeah, that's what I meant.
Yeah.
Okay, thank you.
Does that make sense?
Yeah.
Yeah. So the algebra, look, I sort of went quick. There's no doubt there's a lot of algebra here. And there's I'm using this L'Hopital's rule, which you maybe don't remember. I'm using a lot of stuff. And look, don't get discouraged. Don't say, oh my God, I don't remember anything. I suck. Well, no, you don't suck. This is hard. It's not easy to learn this. I can't emphasize that enough. There's not enough time in the day to be an expert at everything when you're in Calc 2. You can try, but it's just really difficult to master all this. You know, I wish I had a better answer for you. It's time consuming. It's stressful, you know, and not to mention you're trying to do all this insanity with what's going on in this crazy ass world, which I haven't even read anything today. Who knows if we've solved it yet or not? Let's go. How can we look at calculus if we can't solve the coronavirus? I see nothing that we've solved it yet. All right. Okay. So does anybody want to ask any other questions about this crazy example? Okay. It's time to move on then. Some more tests. Fun time. Okay, so what we're going to do now is we now discuss, that's an ugly C. What's an important class of series called alternating series. So one of the things that happens for many different reasons is we arrive at series that alternate. And what that's going to mean is that at each term, it goes from positive to negative. So it alternates. And since these kinds of things arise in many different scenarios, we'd like to study them. And so that's sort of what we're going to do right now. And we're going to start with a very special type. So you guys hear my kid? I don't know what she's talking about. So the prototypical example is the following. So we had the harmonic series before, but now we can ask about the one that alternates. So what is this series? Well, let's write out the right-hand side first. This series is very interesting. It looks like the harmonic series, but it ain't quite the harmonic series, because the harmonic series was 1 plus a half plus a third plus a fourth plus a fifth forever and ever and ever. We want 1 minus a half plus a third minus a fourth. That's what we want to happen. And so what we do is, let's say that's what we want to study. 1 minus a half plus a third minus a fourth plus a fifth. Oh, excuse me. A fifth minus a sixth. You get the idea. And then this pattern continues all forever and ever and ever and ever and ever and ever and ever. And so the first thing we need to do is, how can we write this compactly? How can I write this in our notation with the sigma? So we know that this is like 1 over k. But how do we make it so that it alternates the sign each time? Well, one way to do that is to take advantage of a very fact that you guys learned many, many years ago. And that is, if you take -1 and raise it to an odd power, it's -1. And if you take -1 and raise it to an even power, you get +1. So if I put in the numerator -1 and I raise it to the power k plus 1, then that is what creates the alternating. When k is 1, I get power 2, so it's even. When k is 2, I get power 3, so that it's odd. And then that gives me negative. And then when k is 3, I get a power, an even exponent. And so that creates the, I keep repeating myself, but for some strange reason, when I was trying to learn this, that's, you know, this whole negative k plus 1 thing was very difficult for me to learn. Does anybody have a question about this thing? Okay, so this is the standard example of an alternating series, and it turns out this guy converges. And the question is, why does it converge, and can we say anything about other series that alternate? As you would imagine, anything that alternates is going to have this nice behavior, because every time you give something to it, on the next step, you're taking something away. You give, you take. You give, you take. Does anybody have a question? Okay. So let's go to the next page, and let's state our next test. So in general, an alternating series has this form. So remember, what does it look like? It looks like it's some number, which we'll call a sub 1, and then it's minus a sub 2, and then it's plus its third term, then it's minus its fourth term. You know, this alternates forever and ever. And so what does this look like? Well, one way in which we can write this is we can say, okay, it's the sum. K goes from 1 to infinity of -1 to the k plus 1 power times a sub k. That's what it looks like. You know, or if you wanted it, I mean, it might, maybe it starts negative. Maybe it's minus a sub 1. You know, so if you wanted, you could say it's minus a sub 1 plus a sub 2 minus a sub 3. That's also an example of an alternating series. In that case, you would just modify this slightly. It would just be -1 to the k, a sub k. So again, this is scary notation. You don't need to let it, you know, drive you crazy. That's why I gave you the example first. Try to compare, try to think about these things through the example. And then once you have a better understanding of a specific example, then you can kind of go to these more general ways of describing things. Okay, so here's the statement of the test. So alternating series test. Here's what we need to happen. So if a sub k's are greater than or equal to 0, and so let's sort of think about this before we write it down. What do you want to happen? We know that by the divergence test that these terms have to be going to 0. So we know that has to be the case. But we know that's not enough. So what does the alternating aspect add that just going to 0 doesn't? Well, it adds the fact, what I said a few moments ago, is that every time I take something, or I add something new, in the next step, I'm taking a little bit less away. And so at each step, I'm adding a little bit more, then I'm taking some away. Then I'm adding a little bit more, but I'm taking some away. So that balancing act is canceling things out. So if you have, let me say it like this. It might be a little clear. Get my eraser. So let me give you the three. Let me just write it in terms of two things. Let me write it like this. So if, first off, 0 is less than a sub k plus 1 is less than a sub k. If that's the case, basically this just says each term is getting smaller. And then the second condition is that the terms are going to 0. Then the series converges. So this only going to 0 is not enough. We also need this alternating aspect. If you get that, then you're happy, it works. And that's clearly what happens with the harmonic series. Does anybody have a question about this statement? So here's a cool fact that it's worth pointing out. And we'll prove it later in the term. the alternating series, and you could even go play around with this right now if you're bored. If you take the alternating series, it actually sums to a very familiar number. It equals the log of 2. And many of you know all about the log of 2. It shows up in chemistry and biology all the time, in other areas, because it has to do with half-life or doubling time of things, which is all over the rage right now in the news because we're all worried about how viruses spread and what are the half-lives and all that stuff. So later in the term, we'll see why this is true, but if you don't believe me, just go to a calculator and experiment. You'll say, holy heck, it does. Does anybody have a question? Comments? Concerns? Fun stuff. All right, so look, here's the thing. When is there a pretty obvious sign to use the alternating series test? Anytime you see -1 raised to a power in your series. And we're going to see this. It's going to show up a lot in what we do going forward. If you look at the homework, it shows up a couple times. And so that means you might want to try it there, although you don't necessarily have to. There might be other tests which apply. Okay, so terms with negative, excuse me, series with negative terms. What they do is they suggest we might have, or we might want to sort of think about the harmonic series. The harmonic series diverges because we're adding them all up. But if we alternate and we add, subtract, it turns out it converges. And so what we'd like to do is we'd like to sort of classify series that behave in that manner. And then, because not all of them will behave in that manner, some won't. Sometimes if we have an alternating series and then we replace all the minus signs with plus, we still get convergence. And we'd like to single those guys out. Those series are very special to us, so we like to give them a name. So series with negative terms suggests we might want to single out special types that do converge when we replace minus with plus. So it's hard for us to kind of envision why that's important right now, but it turns out it is very much important. So let me beat these examples one more time before we make this definition. So note, one minus a half plus a third minus a fourth plus blah, blah. This guy converges. But if we replace all these minus signs with plus signs, we get a divergent one. So if we just try to do this, these things aren't much different, yet their behavior is completely different. Okay, so we need the following definition. And these are very important later on, and especially in higher mathematics. So if, okay, so when I say in words, take minus signs and replace them with plus signs. That's sort of just like baby talk. How do I say that in a mathematically sound way? Well, we would say we don't just take the minus signs and put plus signs there. One way of saying that is we take the absolute value. And so if this series converges, if I take the absolute value of each term in the series converges, if this converges, we say that the series converges absolutely. So the new word here is this sort of, was that an adverb or whatever? We say the series converges absolutely. And then if this guy diverges, when the series converges, we say the series converges conditionally. So there's two words here that are very important in mathematics as we go forward. This idea of absolute convergence and this notion of what we call conditional convergence. So if we go back to our harmonic series, the example here is 1 minus 1/2 plus 1/3 minus 1/4, blah, blah, blah. How do we say this? We say this converges conditionally. Because if we take away the minus signs, it diverges. Okay, so does anybody have a question, comment?
Yeah, can you stay there for a quick second?
Stay here as long as you need. Give me time to stretch. I hate sitting down. I need to like figure out a way to stand and make all this more. I should buy one of those big glass things and I can write on it. And then I can see through it. Like I see people on YouTube with those things. Okay, you good, Daryl?
Yeah.
All right. So what do we want to use from this? Well, here's an important consequence. And this sort of just ties in what we've been doing is good enough. So here's an important theorem. I'm not going to prove it or anything. Although we could, it's not a difficult thing to prove. So important fact, absolute convergence implies convergence. And basically what this means is everything we've studied before today about alternating series, you could all call that absolute convergence because those terms are all positive. And so let's write that down. So the fact is, if a series of positive terms converges, it is absolute by default, just by definition. So really the only time that this absolute convergence is really something we're concerned about is anytime we have negative signs in our series or negative terms. Okay, does anybody have a question? Okay, so if you guys don't have a question, we will move on to the next test. So it's always nice to change colors. So with these ideas, we can state even more tests. Okay, so don't forget, if we started where all these tests began, they all began with this so-called divergence test. And if you read what that says, the divergence test says that if any series is going to converge, the terms must be getting smaller as we go further out in the series. They must be going to zero. Now, what that test doesn't say is it doesn't say that if they do go to zero, it will converge. So we need to figure out what are these extra conditions. If going to zero is not enough, then we need to think about what other conditions must we have. Well, the alternating series says if they alternate and go to zero, then it converges. But what if they don't alternate? So what other thing can we do? Well, one option would be, let's study how quickly something goes to zero. Now, when I say how quickly something goes to zero, that's sort of ambiguous, but you can imagine if I go 1, 1/2, 1/3, 1/4, those things are going to zero, that pattern. But I think you guys would sort of quote unquote argue that 1/2, 1/4, 1/8, 1/16, 1/32, you would argue those numbers are getting to zero quicker than 1/3, 1/4, 1/5. They're getting smaller quicker. And so that suggests that if we sort of somehow find a way of quantifying how these terms are going to zero, we might have a better chance of developing useful tests. And so our next test is exactly that. It has a unique way of quantifying how we go to zero. So this is called the ratio test. So take your series, we've been calling them A sub k, and what we're going to do is we're going to compute a limit. And for whatever reason, textbooks like to call this number R. Maybe R for ratio, I don't know, root. So what kind of limit am I going to take? Well, I'm going to take the absolute value of the ratio of the terms. So I'm going to take the kth plus 1 term, and then I'm going to divide it by the kth term. Now I'm going to take that limit. Now there are 3 options for this limit. The first option is that this limit is less than 1. So if this limit is 0 or less than 1, the series converges. the next option is that if this limit is greater than 1, the series diverges. And then the last scenario is that if the limit is actually equal to 1. So if it's equal to 1, the test is inconclusive. We can't use it. You need another test. Now, you can actually, if you wanted to be completely a nerd, and you can actually say that this thing converges absolutely. Because we're taking these absolute values. Okay, so let's get to some examples, because this one is probably one of the most common tests we'll use the remainder of the semester, and it's really easy once you learn it. It actually is, I kid you not. So let's look at some examples. Please interrupt me if you have questions. You guys know that that's all good by me. If I go too fast, tell me to slow down. So let's start with a very popular one. 1 over k factorial. To remind you what k factorial means, it means the following. This is 1/2 plus 1/6 plus 1/24 plus 1 over 120. One of the things you'll learn when you practice these things and do examples is that anytime you see a factorial, the ratio test should be your first choice of test, and more often than not, it'll get the job done. So let's see why. All right, so don't forget, and by the way, well, I'll write this on the next page because I'm going to go to the next page. So let's beat this one to a pulp since it's our first example. Here, let's note that a sub k is 1 over k factorial. And if that's a sub k, what's your kth plus 1 term? Your kth plus 1 term is 1 over k plus 1 quantity factorial. So that's a very important thing to note. So when we go to the next page, we're not completely overwhelmed. So let's compute our number r that we want to compute is this limit.
Can you go back to the last slide real quick?
Sure, yeah. Let me know when you guys are ready.
Okay, you could go ahead now.
All right. So we want to take the absolute value of the k plus 1 term over the kth term. And so if we plug in what these guys mean, the first thing I can note is I don't need absolute values for this particular problem because all the terms are positive. So this is 1 over k plus 1 factorial, and then this is all over 1 over k factorial. That is just me plugging in what each term is. Okay, now what I need to do is I need to remember what we talked about a few slides ago. If I have two fractions and I'm dividing them, I multiply by the reciprocal. So this is equivalent to this. Now what I'm going to do is I'm going to come over here on the side because I need to remind you guys of how canceling factors works. Because this thing simplifies to nothing more than the following. And this is 0. But let's go over here because it might not be clear to everybody why that which I'm going to remind ourselves, this is all in the limit. So I just want to remind you that if you don't quite see the algebra, k factorial over k plus 1 factorial, what is this equal to? Well, this is k times k minus 1 times k minus 2 all the way down to 3 times 2 times 1. And then this is k plus 1 times k minus 1 times all the way down to 3 times 2, etc. And so what happens is everything cancels out. This k minus 1 cancels with this. This k cancels with this. This 3 cancels with this. And everything in between cancels. So only one thing remains. And the only non-factor of 1 is just this. So it might be useful for you to ponder that for different values of k. Maybe you put 8 and 9 there, or 12 and 13, or 26 and 27, but convince yourself that that's the case. Does anybody have a question about this? Comments, questions? Okay, let's look at another example. So let's take k squared over 4 to the power k. So let's write out the first few of these. Let's say k starts at 1 to infinity. You get 1/4 plus 2/16 plus 9 over 4 to the third is 64. So we'd like to know, does this guy converge? So maybe we ask you like this. You might try another test. Maybe that 4 to the power k suggests you want to compare with a p series or something. I don't know. But that would be a bad idea because that's not going to work. But that exponent of k makes me think I might have a chance if I do some ratio test. So let's compute. We'll switch colors again. So what I want to do is I want to try the ratio test. So this time I'm going to skip some steps, and what you'll learn is if you do a few of these, you don't have to write everything out because the same sort of pattern happens each time. I need to take a sub k plus 1 and divide it by a sub k and absolute values. But in this particular problem, the absolute values, just like in the last one, are redundant. And just like in the last one, what I end up getting is I get a fraction divided by a fraction, in which I will write as the multiplication by the reciprocal. So if you think about that algebra, all I did is instead of writing a fraction divided by a fraction, I multiplied by the reciprocal. And what you'll notice, and as you saw in the previous problem, is things will begin to cancel out. So I can cancel this 4k and with the one that's living downstairs. So let's rewrite this. So I'm going to rewrite this. Upstairs I have a k plus 1. I'm going to reorder this thing squared over k squared. And then this is times k to the, 4 to the k. And downstairs I had 4 to the k plus 1, but I'm going to write it as 4 to the k times 4. And then, of course, this 4 to the k cancels with this. And what we're left with is a 1/4 times this limit, which we can, if you don't see what it is right now, you can write it out. Because this limit is just 1. And then how do we finish the problem? We say since 1/4 is less than 1, we have convergence by the ratio test. So that is how you would answer a question like this. Does anybody have a comment or a question about this particular example?
How did you get k squared on the bottom? Like the last slide, you had 4k plus 1.
And how did I get k squared on the bottom?
Yeah, right there.
No. Okay, yeah, but look over here. There's a k squared over here. I'm just switching the denominators.
Oh, okay.
Does that make sense?
Yeah.
Yeah, I just wanted to realign them just so that you can see the cancellation easier. You don't have to do that. In fact, what happens is if you do a bunch of these, you're going to see that the same thing happens in all of them, and then you could just skip a lot of these steps. Now, I'm not saying that's the best way to do it. I'm saying some of you will do it that way. And that's okay as long as you recognize what's happening. All right, does anybody else have a question about this? Okay, now before we go, let's state one more test that is it's pretty much the same thing as the ratio test. It's just useful in some other scenarios. So our last test is the root test. So this is the same as the ratio test, but instead of using ratios, you set R equal to the following limit. You use roots. So you take the kth root of the absolute value of the kth term. So let's look at an example real quick before we leave. I know we're running out of time, but I kind of want to give you one example of this. So let's take, let's say -3 to the power k all over k to the 20th power. So if you write this out, this is -3. Then the next term becomes 9 over 2 to the power 20 minus 27 over 3 to the power 20. Yeah. So this guy converges. And the reason it does, well, if I take this limit, if I take the kth root, so I have it above me, so I can do this. That kth root, if I take the absolute value, the -3 just becomes 3. But all you're left with is the following. You're left with 3 over k to the 20th over k. So I'm kind of, hold on. I misspoke. I'm lying to you. Hold on a second. This does not converge. It actually diverges. My apologies. I got ahead of myself. Now, I'm going to go to the next page, and I'm going to take this limit, and you're going to have to remember some, again, some stuff we learned about in Calculus 1. So if I want to take this limit, I have 3 over this. I want to pull the limit out, the 3 out front. I can do that. So what I have is I really have 1 divided by the following. I have k to the 1 over k power. And this is all what? To the 20th power. So I'm using some exponent rules that you might not remember as quickly as I'm remembering them. But this limit from Calc 1, this is 1. So this is 3 times 1 to the 20th, which is 3. And then since r, which is equal to 3, is greater than 1, the root test says it diverges. So again, this is it's a little complicated. You might want to remind yourself how I'm taking that limit. You might want to remember your old friend L'Hopital. So here's a very important fact that you might want to convince yourself of. The limit as k goes to infinity of the kth root of k, that's 1. So that's what I'm using. And if you want to verify that for yourself, use L'Hopital's rule. But we're out of time, so I don't want to withhold you guys hostage much longer. Does anybody have a question before we end this, or a comment or anything? No? All right, well then I'm going to stop recording now.